All right, good morning, everyone. So this is lecture 12 of 124 Physics 1A. So we'll continue from where we've left off, and then we'll learn the concept of center of mass, which we will need going forwards as we go into rotation. So this is the last lecture. We're still talking about motion and mechanics, but this is the last lecture on linear mechanics. From next week, we will talk about rotational mechanics, rotation of an object. And so knowing the center of mass prepares us for the next topics. But before we go to center of mass, let's revise what we learned yesterday, where we learned. We started this week learning about momentum. We learned that momentum is defined as mass times velocity. Momentum is the mass in motion. And yesterday we learned how to change. We also learned how we can change momentum. So we can change momentum if we change the velocity or the mass. In the previous lectures, we learned the change in changing momentum by changing the velocity. And so we learned that if we change the momentum via the change in velocity, we are essentially having a net force acting on our object, because change in velocity with respect to time is equal to acceleration. And Newton's second law of motion says that if you have acceleration coming from the change in velocity, change in velocity over change in time, then we have a net force. And in our previous lecture, we looked at different scenarios with collisions of how the velocity of colliding objects change, and therefore bringing about a change in momentum. Okay. Looking at the definition for momentum, though, there is a mass component as well. So we can technically also change the momentum by changing the mass of the object. So in this case, how do we deal with the change in the momentum if the mass of the moving object changes in time? Okay, so let's look at this scenario. You have this mass specified by the capital M. It's moving to the right with a velocity v. What if at some instant of time, some small amount of mass is added to this initial mass? So let's just think about, for example, a rock that's rolling down a hill, and as it rolls, it collects some mud. So you have some small amount of mass being added to the already moving mass. Okay. And the small amount of mass being added has some velocity as well, which we designate as small u to differentiate it from the velocity of the moving mass, which is v. Okay. So after some time, the new mass of the moving system will then be a combination of the original mass m plus the small amount of mass, like the small amount of mud that gets stuck on the rolling stone, for example. Okay. And as a result of the added mass, the velocity of this object would also change, right? Because we learned that if you have a bigger object, more massive object, you need more force to keep this object moving. And so if you add mass to this moving object, it's just logical that its velocity will change by a small amount dv. Right, so if we write down then the change in momentum, so this one is coming from net force from Newton's second law of motion, and its relationship to the change in momentum. Net force is equal to change in momentum over time. A momentum, of course, has two components, mass times velocity. So if we expand this basic definition for momentum being mass times velocity and net force being change in momentum over time, we need to get to the derivative of each of the mass and the velocities, because each of them will change over time. So the net force will therefore, the net external force will therefore be the mass times the derivative of velocity over time. In this first term, we are taking into consideration the change in velocity of your object when some mass is added to it. Okay. And then you also take into account the change in the mass because of the added small mass, right, times the velocity. So we're essentially taking the change in velocity in this term, and in the second term, we're taking the change in mass. So here I've listed down what each of the variables and each of the terms mean. Right, dm over dt, that's the rate of change of mass, which, if we think about it, it can both be positive or negative depending on whether mass is being added. Like in the figure here, mass is being added to the big mass. It's the stone that's rolling and mud is being added to it. So of course, the rate of change of mass will increase, will be positive because the mass is increasing over time. Whereas if you think about an object that's rolling, and as it rolls, it disintegrates so that its mass decreases over time, then the rate of change of mass will then be negative because mass is being removed. So dm over dt, that can be negative. All right, let's look at an example to sort of see what each of these terms really mean in practical applications. And a good example of variable mass, or an object whose mass is changing as it moves, is rocket propulsion. Right, so say this scenario here, you have a fully fueled rocket. It has a mass of 21 kilograms overall, so including everything. But of this total mass, so 21 kilograms, this is the total mass. Of this total mass, 15 kilograms is fuel. Okay. Right. What causes the rocket to propel is the burning of the fuel. So what if the fuel is spewed out the rear at the rate of 190 kilograms per second? So fuel is being burned at a rate of 190 kilograms per second. Okay. As the fuel is burned, it's spewed out of the rear end. So this is where 190 kilograms of fuel is going per second. So yeah, you have there your change in mass. Okay, and the burned fuel is spewed at a speed of 2,800 meters per second relative to the rocket. Okay, if the rocket is fired vertically upwards, we want to calculate the thrust. So if you draw the free body diagram of the rocket, you have, of course, the weight force. Every object that has mass will have a weight force or gravitational force that's always downwards. And you have this thrust force, okay, that will propel the rocket upwards. So we want to calculate how much this thrust force is. And as the rocket blasts off in the beginning, where it's fully fueled, we want to find the net force on the rocket. And then after some time, just before burnout, when all the fuel has been used up, we want to find as well the net force. All right, so let's relate this scenario to the equation. So this is the equation for momentum relating to external force, expanded out in terms of change in velocity and change in mass, which we looked at in the earlier slides. Now, I just rearranged this equation so it's easier to interpret physically. So if I put on the left side mass times derivative of velocity over time, okay? So again, when we're talking about derivative in finite time, we can just think, if everything is finite, if the change in velocity is finite and the time interval is finite, we can just think about the derivative as the change in velocity over some time interval. Okay. So yeah, so you can think of this as the change in velocity over some time interval. And on the left-hand side, I just rearrange it so that I just rearrange this equation so that the right-hand side contains the net external force and the change in mass over here. But by rearranging this, we can see that dv over dt, this is just mass times acceleration, because change in velocity over time, we learned that to be acceleration. So this left side, this is equal to mass times acceleration of the rocket. Okay, external sum. So this symbol here is called the summation. Summation means you just add up all the external forces involved. So this is all the external forces on the rocket. That means it includes gravity, air resistance, and all the other external forces acting on the rocket. Okay. This be relative dm over dt. This is what we call thrust, because it's the burning of the fuel that causes the change in the mass of the rocket. Yeah, remember again, this derivative of mass over time, you can also just think of that as the change of mass over time if we're just looking at a finite amount of mass over a finite time interval. So since we are burning the fuel over time, the change in the mass of the rocket is due to the burning of the fuel, and the burning of the fuel gives us the thrust. So this whole expression here, vrel relative velocity dm over dt, is just the thrust. It's the force exerted on the rocket by the expelled gases. Right. Okay, so does each of the terms in this equation make sense? Because it might look very mathematical, but yeah, each of them actually means some physical interpretation. And if we also relate this to Newton's second law of motion, then we can see that on the left side, this is just mass times acceleration, and the whole right side, this should be equal to the net force. So it's, in essence, we're just looking at Newton's second law of motion written down in terms of changing mass and changing velocity. Cool. All right, so are we now able to answer the questions then? So the first question was the thrust, this force that will propel the rocket upwards, which is the thrust force. Right, so from this equation here, we saw that thrust is this whole thing here, relative velocity times dm over dt. Okay. So that's the thrust, relative velocity over dm over dt. Okay, picking out what the values are from what's given. Dm over dt, this is how fast the fuel is burned. Right, the fuel is burned at a rate of 190 kilograms per second. Okay. So that's where you have dm over dt is equal to 190 kilograms per second. It has to be negative because as you burn the fuel, right, you're decreasing the mass. And so that's where dm over dt needs to be negative. vrel, this is the relative velocity. This is the relative velocity of the gases in relation to the rockets. And the problem says that the burnt fuel is spewed out the rear with a speed of 2,800 meters per second relative to the rocket. So that gives us relative velocity is therefore that 2,800 meters per second. Why is it negative? Okay. So as the fuel is burned, the gases are spewed out of the rear. So you have there the velocity of the gases are pointing downwards. And we're working with vector quantities here, so you need to include the negative sign for the direction of relative velocity. Okay. This then gives you a positive thrust, which makes sense because we want to propel the rocket upwards, and so your direction should be positive, and you have this thrust just doing the calculations. All right, were we able to follow the solution here? Okay. Right. Next, we want to find the net force on the rocket at blast off and just before burnout. So first, let's do the blast off part. Okay. So net force. Show. Let's just go back. So when we looked at this equation earlier, yeah, we said that the left-hand side, this whole thing is mass times acceleration, and the whole right thing is the net force. So it includes, the net force includes the external forces, you know, gravity, air resistance, and all of this. And it also includes the thrust force. So net force, if you also look at your free body diagram, your net force consists of thrust, that's upwards, and gravitational pull, that's downwards. So you have two external forces that contribute to the net force on the rocket. So when we then calculate for the net force, we need to try to find the weight force, which is the external force being exerted on the rocket. Okay, so you have these two forces contributing to the net force. So one is the weight force, so that's just mass times gravitational acceleration. Okay. At blast off, we assume that the rocket is still fully fueled. So you have this much mass initially when it's fully fueled, and that's why your mass, so your total mass is 21,000 kilograms, or 2.1 times 10 to the 4 kilograms. Gravitational acceleration is, of course, negative 9.8, giving you this weight force. Right. So the net force will be the thrust. Thrust is upwards, gravitational force or weight force is downwards. So your net force consists of thrust plus weight force. The thrust, we've calculated that from question A, and weight force is what we calculated from M times G. Remember again the negative sign there. All right, does that make sense for net force? Okay, so then just before burnout, how will our solution change? If we want to calculate the net force just before burnout, how should we change our calculation? So net force is still, this thrust minus the weight force, but what will be different? Yeah, before burnout, all the fuel has been used up. So that means the mass of the rocket would be lighter at burnout compared to blast off. So the problem says 15,000 kilograms of fuel is included in this 21,000 kilograms of total mass. So this is total mass, this is fuel. So if we use up all of the fuel, then our mass, see how the mass should then remove the mass of the fuel. Right. So that the weight of your rocket would just be, from the shell, from the rocket itself, without the contribution of fuel. Right. Which should be smaller than what we found earlier. And then again, if you get the net force will again be the thrust minus the weight force. So you have thrust from A minus the new weight that you've calculated without the fuel. Okay, did we follow the solution to this problem? Cool. Any questions about this problem before we move on, or about changing mass in relation to momentum and external force?
So the thrust remains the same.
Yes, we assume this because the fuel is being burned at a constant rate, 190 kilograms per second, and thrust is provided by the burning of this fuel. So we assume that it remains the same. So just before burnouts, we still have like this residual thrust going up, but there will be still a small amount of fuel that has to power this thrust, but we can assume, you know, to some approximation that almost all fuel is used up. And compared to 15,000 kilograms, maybe 1 kilogram is almost negligible. Yeah.
What does the FEXT stand for? I understand what it's doing there, but what does it actually stand for?
Oh, so it stands for external force. External. So yeah, all the forces external, like the weight force and the thrust force.
So you basically change think of the derivative as a delta.
Yes. Yeah. So like, for example, here, yeah. So because we're usually in physical scenarios, we're just looking at finite quantities, right? Finite changes in mass over some finite time. And so we can change derivatives into deltas. Cool. Yeah, good. All right, so up to this point, we've been applying Newton's second law of motion and forces and looking at objects, so as if they are points, right? So although, for example, this rocket, it's expanded, we were still treating it as if it was a point, and we were looking at, you know, the influence of forces of thrust and weight on, like, say, on this point of the object. And this is a valid way of looking at objects. So when we draw a free body diagram, I told you, you don't need to draw like the whole elaborate object. You can just represent it as a dot or a square and draw your forces acting on this dot or square. And that is because extended objects can be thought of as particles as well if we consider the concept called center of mass. So center of mass, this is, it's defined as the average position of all the mass that makes up the objects. In the simplest definition of center of mass is it's that certain point in the object where all of the object's mass is assumed to be concentrated at. So say this pen, or maybe I'll use this. So say this dragonfly here, it's extended, right? It has wings and tails and all of this. So yeah, so the mass of this dragonfly can be thought of to be concentrated only at a single point called the center of mass. And so if we solve problems involving this dragonfly's flight, for example, we can just look at this single point and say, what are the forces being exerted at this single point? That's equivalent to looking at what are the forces being exerted on the dragonfly. And the easiest way to find the center of mass is to find the point of balance. Where is the point where this dragonfly can be balanced? If you, for example, put this here, okay, The dragonfly is balanced like that. So the center of mass of the dragonfly is at that point. You can consider all of the mass of the dragonfly to be concentrated at that point, and that's why the dragonfly is balanced, because all of its mass is supported by the pen. And if you try to balance the dragonfly at any other point, it won't work. Yeah, it will surely fall down. Yeah, this is right. The whole dragonfly, it's a broken wing one. If you try to balance this out, it won't work. So the broken wing totally changed the position of the center of mass of this dragonfly. All of the mass is no longer concentrated at the center here. You need to find, again, the new center. I've never tried finding the new center of mass of this broken dragonfly, but yeah, you can. So that one way of finding the center of mass is trying to find where the balance point is. Right, so now let's learn how to deal with different objects considering their center of masses. You will see a term called center of gravity. So I'll just address this, just because when, for example, you're doing some Google search or looking at the textbook, you will see something like center of gravity. This is essentially practically to some extent the same as center of mass. If the object, assuming that the object is not so large, the center of gravity is to a good approximation at the position of center of mass as well. It's probably a more intuitive description because it's where gravitational pull is acting at the object. And so if you balance the object at the center of gravity, then the gravitational pull downwards balances out the normal force that's upwards. So center of gravity is just another term. You can consider it as another term for center of mass. So with extended objects, that's how you find the center of mass. Where does it balance? Okay, mathematically, if you have several particles or several objects, this is how we find the center of mass. It's defined by this mathematical equation here. So in this particular figure here, you have 4 masses, M1, M2, M3, M4. Each mass is located at some position compared to a reference position. So let's say this is some origin or reference point. Okay, if the masses are located at these positions, we can measure their positions relative to the origin. And let's say the position of M1 is R1 away. M1 is R1 away compared to from the origin. M2 is R2 away from the origin. M3 is R3 away from the origin, and M4 is R4 away from the origin. So in this case, then we interpret this. So this is the summation symbol. It means that the center of mass is the sum of the mass times position of each of the particles. So I here, so yeah, I is the index for a mass. N is the number of masses whose overall center of mass you want to find. Okay. So capital M here, it's the sum or summation of all the small m's. So that means M is also the total mass. Okay. Right. So for these particles here, if you have 4 particles, let me expand this. Seemingly, maybe it looks like a scary one, but if you expand that, then the center of mass of the particles will be the sum of M(I)(Ri). That means M1 R1 plus M2 R2 plus M3 R3 plus M4 R4, because there are 4 particles here, 4 objects, 4 masses whose overall center of mass you want to find, divided by the sum of all the masses. That means mass 1 plus mass 2 plus mass 3 plus mass 4. Right. Okay, so this is how we interpret this, this short notation for the definition of finding the center of mass. Now the R, this is just a general position vector. Okay? It's a general position vector for these R's. If you can see, they are all diagonal. Right? And we've been learning that if you have a diagonal vector, you can always decompose your diagonal vector into X and Y components. So if we rewrite this definition for the center of mass R, then we can just look at each of the X, Y, and Z components, so that we can use the strategies we've learned of breaking down a diagonal vector into X and Y components. So we can find the position of the center of mass along the X-axis by doing the summation of mass 1 times its position along the X, mass 2 times position along the X, mass 3 times position along the X. So this X here means position along the X-axis. Of course, then Y will be position along Y-axis, and Z position along the Z-axis. But I think for now, we'll just use 2-dimensional center of masses. Okay. All right. So the easiest way to maybe apply this is to look at an example and see how we apply this. So we want to find the position of the center of mass of these 3 masses. Say you have mass 1 at this position at the origin, 0 I hat plus 0 j hat. Mass 2 is located somewhere here. The position coordinates are 4I meters. So this is meter, the unit, plus 2j hat meters. So 4 meters to the right and 2 meters upwards is the position of R2. R3, 50 kilograms, its position is 4 meters to the right and 4 meters down or below the origin. That's why you have a negative sign here. Okay, how do we find the center of mass of this overall center of mass of these objects? The answer is 2.1 along the X and negative 0.59 along the Y. Okay. All right, let's look at this, how to solve this. Yeah, if we can see here, the positions, they have X and Y components. So that gives us a clue that we need to find the center of masses in component form. And usually this is usually a recipe as well. Find the center of mass along the X by considering the X positions, then center of mass along the y by considering the y positions. So let's do center of mass along the x. Okay, you have 3 particles, so that's just m1 x1 plus m2 x2 plus m3 x3. So m1, this one has a mass of 90 kilograms times the position along the x of m1 is 0. So I'll write it down even if it's 0, just so we can see the direct application of the equation. Now m2 times x2, m2 has a mass of 45 kilograms and its x position is 4 I hat, so times 4 meters. And for x3, m3 is 50 kilograms times an x position of 4 meters divided by m. This is again the total mass. Right. So we do 90 kilograms plus 45 plus 50. And this is how you get the number 2.05 meters, which we can approximate to 2.1 meters. Okay. For the vector form, the center of mass along the x should be 2.1 meters, and then add the direction. The fact that you got a positive number for finding x, that means that will be a positive I hat direction. And you do the same thing for the center of mass along the y axis or y component. So m1, again, 90 kilograms times the position along the y is again 0, plus m2, it's again 45 kilograms. Position along the y is 2 j hat, it's positive. So that's just a times 2, plus m3, 50 kilograms times, this time the y position of m3 is -4. So you have to include the negative sign when calculating the position of the center of mass. Yeah, you need to include this negative sign. Again, divide this with the total mass, 90 plus 45 plus 50. Okay, giving you a center of mass position along the y as -0.594 meters. In vector form, the y position of the center of mass will be -0.59 j hat meters for the unit. So we're talking about position. Right. So therefore, the overall position of the center of mass, so R, vector R now considers the x and y components. So the overall position will be 2.1 in the I hat direction minus 0.59 in the j hat direction. And don't forget the units. We're talking about position, so that will be a unit of meters. So that means if you wanted to balance this thing out, you balance it somewhere 2.1 meters to the right, somewhere here, and 0.9 meters downward. So maybe around here. So this is the center of mass or balance point for these 3 objects here. All right, so for discrete particles or discrete objects, this is how we find the center of mass. For symmetric geometrical objects, it's relatively simple. If your object is symmetric with uniform density, then the center of mass is exactly at the geometric center. And you can see that. For example, this is a rod. You can consider this as a rod. You can usually balance it at the middle. Yeah, at some point. Somewhere in the middle, you can balance a stick, for example. So for geometric figures, it's at the geometric center. For symmetric figures, symmetric objects, the center of mass is at the geometric center of the object. Okay. Can you tell me where you think the center of mass of this ring will be located? So it's a hollow ring. So this one is solid and that's a hollow. Yeah, it is symmetric. It's a symmetric object. So the center of mass will be at the center of the hole. So it is possible to have a center of mass that is outside of the object. I have some. So this is one example where the center of mass will be outside of the object. So we'll try to see it's a like an L-shaped object, okay, that you want to balance. For example, you're building some architecture and you want to balance this L-shaped beam. You need to find, of course, where the center of mass is in order to know how to balance this. How do we find the position of the center of mass of this extended object? We know that for symmetrical objects, the center of mass is at the geometric center. For this extended object, so you can always divide it into two symmetrical objects, right? If you, for example, divide it here, then you're just looking at two rectangles. Okay. So you can find the center of mass of each part. Okay. And then once you've found the center of mass of each part, you can consider those center of masses as point objects. And then you can find the center of mass as if those point objects are systems of particles, like what we've looked at with those three masses in the earlier example. Right, so let's try to do this. Okay, so yeah, let's divide this thing into this rectangle and another rectangle is this one along the horizontal. You can, of course, divide it this way, but let's just do this division. So that rectangle A is 3 meters by 9 meters and rectangle B is 6 meters by 3 meters. Okay, where's the center of mass of rectangle A? Some coordinates. Yeah, it should be in the geometric center. Yeah, if this is somewhere here, correct. Yeah, somewhere in the middle between these 2 points and middle between these 2 points. Cool. How about for rectangle B? Rectangle B is this 6 by 3 meter thing. Where is its center of mass located? We're using this as the origin, so we're measuring positions relative to this point. Yeah. Wouldn't it be 6? Yeah, 1.5. I'm sorry, this will be 3. It will be somewhere here. Right. We're just looking rectangle B. It's just this bit. So the center of mass of just that bit will be at this center here, correct? Yeah. So then we can just totally forget about the extended rectangle and just consider these 2 points with these coordinates, with this position coordinates, and try to solve the position of the center of mass along the X and position of mass, center of mass along the Y. So we're just looking, it's as if you're just looking at these 2 objects here, MA with mass MA for this A rectangle and mass MB for this B rectangle. Of course, you also need the total mass. Okay. The problem here is we know the coordinates. We can figure this out because it's just in the geometric center of the rectangles. But how about the masses? We don't know, we're not given any mass. The idea is what's really needed is how the mass is distributed over this extended object. So the mass should be uniformly distributed over the total area of this object. So the total area is 45 square meters, taking the area of rectangle A and adding that to the area of rectangle B. So the total area of this extended object is 45 meters squared. The mass for each rectangle should be proportional to how big the rectangle is. Right? So the amount of mass in rectangle A should be a proportion of the area of rectangle A to the total area of the extended object. Right? Does that make sense? Okay. And similarly for rectangle B, the mass, how much mass rectangle B has should be in proportion to how the area of rectangle B is compared to the total area of the extended object. Okay. Right. So we can think of the mass of A as 0.6 and the mass of B of 0.1. The actual mass doesn't really matter whether it's 25 kilograms or whatever, because as you can see here, mass here, it's just really a ratio of the mass of A to the total mass of B to the total mass. Okay. Right. So for the position along the X, we have the ratio of mass for rectangle A, which is 0.6, times the position of the center of mass of rectangle A along the X, which is 1.5, plus the ratio of mass for rectangle B, which is 0.4, times the position of the center of mass of B along the X. Okay, divided by the total mass. That gives you a position of 3.3 meters along the X. And you do the same thing for the position of the center of mass along the Y. 0.6, again, the mass for A times 4.5 is coming from the position of this center of mass of A. Okay. And for rectangle B, 1.5 is coming from the Y position of mass B, of the center of mass of rectangle B. Right. Did we follow how we did this? Okay, so the position of the center of mass will be somewhere here outside of the object. All right. And finally, once we know the position of the center of mass, we can then find the speed, the velocity of the center of masses by taking the derivatives. So I will not go into the details how we derive it. It's just taking the derivative. Change in position over time is velocity. And so if you take the velocity of the center of mass, it has the same form as taking the center of mass. It's still mass times the velocity of that mass plus, it's like taking the position of the center of mass, except that instead of using position, use the velocities. And then we can also relate this to momentum, because momentum is equal to mass times velocity. Then the momentum will be the mass times the velocity of the center of mass. And we can also take some form for the force, because force is just mass times acceleration. It's just taking the mass of each of the center of mass components. So we will just do in this course, there's just a question in the workshop about finding the velocity of the center of mass, in which case you use this equation here. But I showed this equation, and just the key takeaway is it's as if the force is acting on the center of mass. And that's why even if we considered extended objects like the rocket, we were just looking at a single point and considering what is the effect of the external force on that single point. That point is where the center of mass is. All right. Yeah. So in the workshop, we'll just do the practice on defining the velocity of the center of mass. So we run out of time, or we can look at this in the next lecture. But yeah, have a good day, everyone, and I'll see you in the workshop tomorrow.